Okay, so today we are going to begin a new chapter and possibly one of the most important chapters in the course. So the chapter is called process. Till now, so while talking, we have been using different words like say program, job, etc. Those things will converge today and henceforth we will use this term process. So let's understand what process is. Make sure you pay attention because this chapter, if you don't understand, you will have lots of problems going forward in the course. So you'll understand what is a process and what is the structure of a process and so on. Let's see. A process is a program in execution. So we have been discussing this multitasking model where there are different, till now we used to say different programs in the computer's memory. And at any point of time, one of those programs is executing. Henceforth, we will use the term process. That is the technical term. Right? So a process is a program in execution. At any point of time, there are several processes in the memory of a computer, and at any one point of time, one process is executing. So you understand that different processes can be in different stages of execution. One will be executing, others will maybe waiting or something like that. We will soon see. And the CPU switches rapidly between these several processes. So we discussed this model that maybe say there are 10 processes in your system and let's say all of them are ready to execute. For simplicity, we can say that the CPU will divide 1 second into 10 parts and will allocate 1/10 of the second to every process. Of course, things are not so simple because the operating system or the kernel itself has to run also, right? So like it's not so simple as 1 second will be divided into 10 units and given to 1 unit given to each process, because every time a process switch happens, the kernel has to run for some time. We will come to that. But essentially, I hope you have got the idea that different processes are simultaneously there in the computer's memory, but at one point of time, only one is executing. And CPU switches rapidly between several processes. So we use the term concurrent while we describe these things. So we are not saying the processes are executing simultaneously. That would be wrong to say because in a uniprocessor system, only one process is executing at a time. Right? But we say that the processes are executing concurrently because if there are certain processes in the system, the CPU is switching rapidly from one process to another. So that every process itself thinks that that is the only process running. But actually, the several processes are running concurrently. Now, what is the difference between a program and a process? A program is a passive entity, like what you write, a C program. And a process is an active entity. So a program becomes a process when the code is loaded in the memory and is ready to execute. So essentially, in a process, you have not only the code, that is not only the program, but also the different variable values and these information, like say at this point of time, the execution has been till which instruction and so on. Right. So that is the difference between a program and a process. A program is a C program, a source code file, which you write, let's say C, Java, Python. But when this program is actually executing, or okay, I should not say executing because not every process is executing at a point of time. But when this program is loaded into the memory and it has its associated variable values and say this, the stack, like maybe you have made a function call. Right, so somewhere it needs to be remembered that a function call has been made and the control should go back to the main function once this function is over. So all these information together, that is what makes a process. Now the last line, see the last line of this slide. Each execution instance of the same program is a separate process. So what do you mean? Can it happen that the same program is running as multiple processes at one point of time? or the same program, so multiple copies of the same program are loaded as different processes in the memory at the same point of time? Can it happen? Does it usually happen? What do you think? Multi-threaded processes. Oh, no, 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 no. Let's not go into complicated things. I don't know what thread means right now. Right, so uh, uh, understand my question. Do you think it is a common phenomena to have multiple instances of the same program loaded in the memory as different processes? Do you think it's a common phenomenon? Okay, Rajat says yes. So Rajat, can you unmute yourself? When does this happen? Like, can you give an example?
Sir, when a program calls the fork function, it creates a child process of itself, which has the
Okay, okay, Rajat,
data.
Rajat, again. See, what you are telling is right. But again, I don't want to go into more complicated stuff right now. From common knowledge, from what we do every day, from what you people do in the lab every day, is this a common phenomenon or not?
Yes, sir, we do open like multiple instances of the same, let's say the same web
Exactly.
browser.
Right. So yeah, I can see some other answers also, like Nisarg has said. So true that, let's say we often ourselves open multiple instances of a program, let's say a browser, right? Also, yes, Aryan mentioned a good point. Let's say all of you are doing the lab, the PDS lab or the algorithms lab. So I guess all of you are using Vim or gedit to write a program. So understand that. This is what Mainak is also telling. So think about Vim or gedit. That is a program, right? Gedit is a program. But all of you are running gedit at the same point of time. So that means what? The code is the same. It's the program, gedit. But all of you are running different processes which are using the same program. Okay. And what is the data of gedit? Can you tell me? What is the data of gedit? So let's say you are using gedit to write a C program. What is the data for this particular process? Or let me change the question. 10 students have logged into a server like you do in the ZPDS lab or Algor lab. 10 or 100 students have logged in. All of them are using gedit to write a C program. So I'm saying that the program is the same gedit, but 100 instances or 100 processes are running. My question is, what is the data of every process? Let's say the process that you are running, a particular student. Exactly what Satwik mentioned. The file that you have opened, that is the data for that process. So actually your program, let's say you are writing a C program. Your program is the data for gedit, that process of gedit. Okay. So understand this again, let me repeat. Suppose a lab is going on, 100 students have logged in into a server. All of them are using gedit to write C programs. Then there is only one program being executed, which is gedit. The source code is the same, but 100 students are running 100 processes. Each process has the same code, that of gedit, but the data are different. So every student, the process run by a particular student, for that process, the data is the file which is being written by that student. Okay, so I hope the difference between process and program is clear. If not, ask. Like this is something that you need to understand. Okay, so Basically, program is a passive entity and process is an active entity which contains the program as well as all the data and this kind of information, like till one has the execution been done, then the stack, state of the stack, and so on. Now, we have used these terms, job, process, etc. Let's just understand a bit more. So in older days, we discussed batch processing or multi-programming systems. Right? So we had a part where we discussed some history of computers. There we discussed these kind of systems. So in those kind of systems, user programs are called jobs. And there used to be a long-term scheduler, a particular software, whose task was to load jobs into the computer's memory. Right. By the way, so we assume that whenever for a program to run, it should be in the memory as a process, right? So who does this? A part of the OS, a part of the kernel. Let's say here a long-term scheduler loads jobs into memory. Now, also you can think of process scheduling as slightly different, where there is another scheduler called short-term scheduler that allocates CPUs to one of the jobs which is in the memory. Right? So let's see this picture. This might make it more clear. So let's say there is a job queue and the long-term scheduler does job scheduling. That means it decides which jobs to put in the computer's memory. And once a job is put into the computer's memory, it becomes a process. Now, let's say there are 10 processors in the computer's memory now, but at a particular point of time, only one of them can run. So who decides which process will run? Who decides which process to allocate the CPU? That is done by the short-term scheduler. Okay, so we sometimes differentiate between these two types of scheduling, job scheduling and process scheduling. Okay, so that is, I hope what is a process is clear. It's basically a program in execution or a program in memory at least. A program loaded in memory along with all the data, control information and so on. So now let's understand the structure of a process. So this is exactly what we were discussing. What does a process contain in memory? So it contains, okay, Satvik has a question. Yes.
Sir, in the previous slide, when job scheduler and process scheduler were there, you've mentioned that the process scheduler, the job queue decides which goes into the memory, but where is the job queue present, like, if it's not in memory itself?
Okay, that's a very good question. So, okay. Now the job queue, okay, see, so you are asking the physical device where the job queue is. So you can think of, let's say, a simple answer would be the job queue may be a part of the disk, right? Because I mean, maybe some of you who have configured a Linux system know something about swap space, etc. Anyway, so maybe a part of the disk itself can be used as an extension of the memory. This is a very rough way of putting it, but yeah, I mean, yeah. So maybe the jobs are there, and from there, a long-term scheduler brings them some jobs to the memory.
Okay, sir.
This is not the only possible answer, but yeah, I mean, maybe one of the answers.
Okay, sir. Thank you.
Okay, so let's proceed. Yeah, so we were discussing what are the parts of a process in memory. So one part is clearly the text, that is the program code. Right? Next is the data. And by this data, we usually mean the global variables. Also, we have the heap where you can, I mean, if you dynamically allocate memory, then memory is allocated from this part, the heap. Also, I think you know there is a stack where you will store the temporary data, function parameters, local variables, return addresses, and so on. right? And I think we know that the stack grows down, the heap grows up. Okay. So basically, this is what you may think a process looks like in memory. This has the text, which is the program code, the different types of data, global, local, also the function parameters, return addresses, and so on. Also, it has this heap portion, which is actually, I mean, if you do not dynamically allocate any memory, then this part is empty. But yes, if you dynamically allocate memory, then it will be given to you from this portion, the heap. Apart from this, anything missing in this picture? Anyone can think? I mean, something which should be there in a process but is not shown in this picture yet. Yes, good point by Aryan, the program counter. So somewhere someone has to remember again that which is the next instruction to execute. So the program counter should be maintained. Then again the CPU registers, then open files. Maybe you have opened a file. So it should be remembered that which files have already been opened, or maybe which file has been opened in read mode, which file is in write mode, and so on. Also, most important, the program counter should be there because, I mean, again, the CPU needs to know which is the next instruction to execute. Right? So those information should also be maintained. So basically, a process is this part in memory, a portion of the memory which is maybe allocated to your process, and that has stored all these things: the text, the code that is being run, the global variables, local variables, open files, dynamically allocated memory, and so on. Okay. So that is the structure of a process. Okay. Now, the next thing to understand is the process states. So a process has different states, which we will discuss. At a particular point of time, a process may be in one of several states. And processes change states based on certain events. So you can think of this process execution as a automata. So I'm sure you have read things like finite automata and all. So there are different states, and a process can be in one state, and there are very defined state transitions, as in when should one process go from one state to another, right? So let's see what those states are, and we will actually show this as an automata, like a state diagram. So see, these are the states. First, let us understand what the states are, then we will see the state diagram. So new, that is, the process has just been created. So let's say it has not even started execution. The process has just been created in memory. Next is ready. The process is waiting to be assigned to a processor. Okay, so I have a question here. Like, is it possible that a state is not, I mean, a process is not ready to be assigned to a processor? When can this happen? I mean, the answer is there in the slide itself, but still, can it be that there is a process in memory, but it is not ready to be assigned a processor? Okay, so exactly what Abhilash and Rajat said. Yeah, Satvik also, Nisarg. Maybe the process is now waiting for some event. For example, it is waiting for user input. So unless that input comes, there is no point in assigning the processor to this process because it won't execute, right? So if you see, there is this state called waiting. Right? So the process is waiting for some event to occur. So the kernel remembers that. Let's say, I mean, as we have been discussing, the kernel, let's say, needs. So there are lots of processes in the system, in the memory, and at one point of time, one process will be executed. So the kernel needs to decide which process to execute next. So it has to know also that which processes are at all ready to be assigned a processor. There is no point in assigning the processor to a process which is not ready. Right? So you have these states like ready and waiting. Also you have the running state. That means actually the CPU has been allocated to this process and that's instructions are executed or being executed on the CPU. So that is the running state. And there is a terminated state, which is the process has finished execution. Also, note this thing. This is exactly what I was telling a few minutes back in answer to a question by Satwik. There is a separate area in the disk called swap space. Sometimes, like say there are lots of processes in the memory. We don't want to keep so many processes in the memory. So then we might, switch or swap in and swap out a process between this main memory and this part of the disk called swap space. Right? So a process need not always be in memory. Sometimes, let's say there are lots of processes in the system. So the kernel is not being able to fit so many processes in the system. So maybe some of the waiting processes, let's say, the kernel decides to swap out to the swap space. Because no point in giving resources or memory to that process while it is still waiting for some input. Because clearly that won't run. Right? So let's say, simplistically that let's say a process which is waiting for input for a long time, or maybe which has asked for a big output to be printed. So unless that has been printed, there is no point in allocating resources to this process. So in such cases, the kernel can decide to swap out a process from the memory to the disk. And for that, there is a designated place in the disk called swap space. Okay, so these are the states. Now let us see the state transitions. So this we are going to see a state transition diagram. This is also called process state diagram. So initially a process is new. Okay. At some point it becomes ready. So ready means it is now ready to be executed on the CPU. It does not immediately mean it is executing, but it is ready to be executed. So if it is allocated the processor, it is ready to be executed. Then let's say the scheduler actually allocates the CPU to this process. Then the process state changes to running. Okay. And then when let's say the process completes, right, so then it becomes terminated. Okay. So this is the simple flow of a process. Let's say in a very old systems where there was only one process running or one process in the memory, then this would be the process state diagram. A process would be created newly. At some point it will become ready. Then the CPU will be allocated. It will run. It will complete running. It will be terminated. But nowadays systems are not so simple because we know we want to have many processes in the memory. We want to utilize the CPU and memory better. And therefore we go for multitasking. And therefore we have lots of other states. Let's see them. First of all, when a process is running, it can become not running at some point and go back to the ready state. And so this slide here says interrupt. Have we discussed this earlier? So this transition from running to ready, so it says interrupt. Have we discussed this earlier?
Yes, sir.
Okay, so fine. The one who spoke, can you give some details where? So what kind of interrupt we were considering? Okay, yeah, Preet Kumar has given the answer. So if you remember, we discussed about timer, right? So That is an exact situation where a process was running, the CPU was allocated to it, but then the timer interrupted, and then the kernel started running. So what happened to this process? The state of this process changed to ready. Because that process could still continue running. It is still ready, but it is not running anymore because an interrupt has occurred. So the kernel is running now. So that is the transition from running to ready. Also, other transitions are possible. There can be the state called waiting, right? And as we discussed, that let's say a process is running, then the process asked for IO. So it will be moved to the waiting state. And when that IO completes, or when the event for which the process was waiting completes, then it will go to ready again. Okay. So again, see, this parts also we have discussed. Now hopefully we'll be able to connect back with what we have discussed. This transition from running to waiting to ready, this is, let's say, the process voluntarily giving up control of the CPU because the process has asked for an IO or some event. So the process as if is voluntarily giving up control. So then the kernel starts running, and yeah, through some syscall maybe also. So the process voluntarily gives up control of the CPU. The kernel starts running, and this process is placed in the waiting state. When that event completes or the IO completes, it will go back to the ready state. And this transition directly from running to ready is when the process involuntarily is interrupted, as in the process did not give up, the process did not make any syscall, or the process did not ask for any IO or service from the kernel. Rather, some external event happened, maybe a timer interrupt, and then the process shifted from running to ready. We have discussed both these situations, if you remember. Also, there is this other process, which other state, which we discussed, that sometimes it may be that there are so many processes in the system that they cannot all be fit in the memory. So then the kernel may decide to swap out a process from the memory to the swap space. So if suppose a process is ready, now it was swapped out. So this will be in the swapped out ready state. Or maybe the process was in the waiting state, then it was swapped out, so it will be in the swapped out waiting state. Okay. Also, it may happen, so see, from waiting to ready, there was a transition that when that event for which a process was waiting completes, the process becomes ready. Now, suppose the process while waiting was swapped out. Now that event for which the process was waiting may be completed now also. So even in the swapped out waiting state, if the event completes, then the process will go to the swapped out ready state. Okay. Okay. One transition is still missing. Can anyone point out what? Exactly what Rajat has said. So this will swap out, right? So from the memory, the process was swapped out to the swap space. So there should be a mechanism to bring back the process also, right? So this is called swap in. So this is the kernel actually bringing in a process from the swap space to the memory. Right. So this is the complete state diagram. Any questions? Okay, good. Fine. So we have discussed the process states. So now, so let me ask a question. Why do you think the state of a process will be remembered? I mean, so every process will be in one of these states, right? So why do you think it will be remembered that which process is in which state? I mean, I'm not looking for a technical answer. I'm looking for an intuition. That why do you think the state of a process would be noted down? Okay, Aryan says kernel's memory. Good answer. Okay, Srijan says main memory. Okay, main memory is a bit fine. Like, I mean, okay, everything is in the main memory. So maybe I was looking for a bit more uh, specific answer. Okay, see, there are basically two choices intuitively. One is that, so we understood that, okay, one is what Aryan said, that the kernel may remember somewhere in its memory. So let's say the kernel has a variable for every process which stores the state of the process. Okay. Of course, there are questions like how many variables to allocate because the number of processes can be huge, right? It can change with time and so on. So the other choice is that every process is already being allocated a part of the memory. If you go back, this is what we discussed, right? So every process is already being allocated a part of the memory. So can the state be stored here? What do you think? Okay, Aryan, so can you unmute yourself? Why do you think it's the kernel's memory?
Because at that time kernel is running, it can control its memory but cannot use the process's memory.
Okay, fine. Yeah. Right. So basically, right, because see, we again discussed that not always the process might be in the memory even. Sometimes it might be swapped out and all. Okay. Okay. So the I think by this discussion, some of you have understood, and it's good to see some of you already understood, and hopefully others also understand that the state of the process somewhere needs to be remembered by the kernel. Yeah. So where is that exactly stored? It is stored in a structure called process control block. So let's see what it is. So each process is represented in the kernel as a PCB, also called the task control block, and it contains many pieces of information associated with a specific process. For example, what are there in a PCB? These are some of the things. The process state. This is what we were discussing. So whether a process is in running state or waiting state and so on. Then the program counter, location of the instruction to next execute. Content of CPU registers. Right, this is what is defining the current state of the process, as in, uh, I mean, um, the variable or the values needed to actually run the next instruction. Those are the CPU registers. So those things are stored. Then CPU scheduling information. So, okay, this part might not be completely clear now. We will discuss this in detail. Basically, like there was a question in a previous class that will every process be allocated the same time every day, every time it is allocated the CPU? The answer is not necessarily. For simplicity, you might think yes, but not necessarily. So often priorities are associated with a process. So that will decide how much time it will be allocated to the CPU. I mean, for how much time will the CPU be allocated to this process? So these things are stored in the PCB. Then memory management information. Again, these terms will not be very clear right now, but just to give the intuition, we have discussed that if there are many processes in the computer's memory, then somehow the kernel needs to remember which part of the memory is allocated to which process, because it cannot allow one process to access the memory of some other process. So that kind of information as to which part of the memory is allocated to this process, that needs to be stored. Then many accounting information needs to be stored. The CPU used, clock time elapsed since start. So have any of you ever tried to figure out how much time your program took to run? I guess in the algorithms lab or anywhere. How much time your code is taking to run? Yeah, so those kind of information, someone needs to remember them, right? So the kernel does all those accounting for every process. Then again, IO status information like list of open files, etc. So all these information are needed or are kept by the kernel. This is the bookkeeping part. The kernel notes all this information about every process so that it can run every process smoothly. And all this information are kept in this kind of a structure called PCB, the process control block. So now, okay, so this picture is fine. Okay, we are showing a pictorial representation, but actually what is the PCB? What do you think? Like if I actually going down to the implementation level, what do you think? How will the PCB be stored? Like in the code of the kernel even, how will the PCB be stored? Okay, Nisarg, very good answer. It will be stored as a structure. Okay, so in Linux, a process is represented as a structure, task struct, and that contains all these different fields. Again, maybe these fields won't be clear right now, but they will become more clear as we go ahead in the course. But as you see, there's a long state. So the state is noting the state of the process and so on. Then there is every process has an identifier. There is an underscore missing here. PIDT is the type, data type. Okay, so there is every process has an identifier. Right, so basically there is a C structure which is storing all these information about a process. Okay, and basically, so there are lots of processes in the system. For every one of those processes, there is a structure, and the kernel is maintaining all these structures so that it maintains which processes are at what state and so on. So Moinak, if you have anything to add, please feel free.
Okay, so not particularly, but one thing to remember is that for each process, so when you say that a process is running or when you are doing ./a.out, you are doing s8, something, anything, always remember what kernel actually does is just create a predefined data structure and start assigning values to the elements of the data structure. That is the simplest mental model that you guys should have. So this is what creating a process means. Kernel will create a particular data structure and then do their magic while repopulating or populating the elements of the data structure.
Right.
That is mostly it. Yeah.
So basically, if you think a process has these two representations, one is in the memory, which we showed like in a picture like this. Right. So that is the part of memory allocated to a process. Plus, for the implementation level, it has this kind of a structure that is in the kernel with the kernel that contains all the bookkeeping information of the process that is needed for the kernel to run the process. Okay, so these are the two parts of the, or the two representations of a process. So as Mainak was telling, when a new process is to be created, the kernel has to allocate this kind of a new structure, and then it fills in the data, and possibly it will allocate some memory to the process. And of course, the information about that memory also will be stored in this structure. Like that's why you had fields like these, like memory management information. So which part of the memory has been allocated to this process? That also the kernel will note down in this structure, the PCB. Okay, so this process has these two representations. One is in the memory, the other is within the kernel, the PCB. Okay, so any questions? Feel free to ask. Okay, if not, let me go ahead. So now that you have understood what the representation of a process is, let us get back again to what we have discussed earlier, context switch. So say one process is running, some way that process will stop running and some other process will start running. Now, how will that happen? Okay, Abhilash is asking where is the PCB stored? That is stored in the kernel space. That means that is part of the kernel. So let's say the part of the memory which is the kernel is using, that the PCBs are stored there. Okay. Remember the kernel has also, the kernel also needs to run, right? So the kernel also has memory. It needs the CPU to run. Don't think that the kernel is a magic kind of entity. It's not that. The kernel also has memory. The kernel also needs the CPU to run and so on. So that is the exact thing that we will see more clearly right now. So suppose we have 4 programs. Okay. So we are assuming that there is no, I mean the processes are independent. So there is no, dependency among them. Also the processes run sequentially. Right. So each process is independent, running sequentially, like the programs that you have written in PDS Lab. Now, only one program can be active or running at any one instant. This is what we have understood till now. So the CPU's point of view is this, that okay, at some point I'll run A, at some point I'll run B, at the same next instant I'll run C, again maybe I'll come back to B, again D, and so on. This is how the CPU's like if you think of from the point of view of the CPU, that is what is going on. At some point, I mean, the CPU is very quickly switching from one process to another. However, the process point of view is different. The process point of view is that every process is running independently and sequentially. So every process can think that I am the only process running in the system. And I mean, whatever I am getting, whatever whatever service I want from the CPU, the kernel, I'm being given that. So every process can think that I am the only one running. However, if you now actually see what is happening with time, so this is what you see. At some point of time, A is running. Maybe the next time instant B is running. Then maybe C, then B again, then D, and so on. Right? So this is what actually is happening with time. This kind of a diagram where time is in the x-axis and you show which process is running at what point of time, this kind of a diagram is called a Gantt chart. So how to interleave processes? That means how will this be managed that the CPU switches to another process? First, the kernel needs to save the state of the old process and then load the saved state for the new process via a context switch. So what do you mean by context of a process? That is the PCB. Okay. So basically, when we say that the kernel saves the context or state of the process, basically it gives some information in the PCB. That's what were the states, what were the values of the CPU registers? Then what was the program counter? Which files were opened? What was the memory allocated to this process? And so on. So this is the saving the state of the old process. That means refreshing these information in the PCB. And then it will load the saved state for the new process. From where will it get the saved state? From where will the kernel get the saved state for the new process? New process means the process that is to be run next. Again, PCB of that new process. Remember, every process has a PCB, right? So how will the process, how will the switching go on? Let's see. So suppose process P1 and P2, we are considering these two processes, and of course we have the kernel also. At this point of time, let's say P1 is running. So the kernel is not running and P2 is not running because P1 is running. Now at some point, let's say a context switch is needed, maybe because of a timer interrupt or something. So then a timer interrupt happens, then the kernel starts running. What does the kernel do? Save state of P1 in PCB1. Then restore state of process P2 from PCB2. And then kernel hands over the CPU to P2. At this point, the kernel stops running and P2 starts running. See, at any one point of time, only one process is running, either P1 or kernel or P2. We are never telling that at the same point of time, two processes are running. So one thing you understand that while switching from P1 to P2 or any switching, the kernel needs to run for some time because the earlier process, the state needs to be saved, and the next process to be run, that state needs to be loaded and so on. Again, later at some point it may happen that the switch, there will be another context switch from P2 to P1. Again, for some time the kernel will run and then P1 will again start running and so on. So this is how a context switch occurs. Okay, there are a lot more things to discuss about processes, which we will continue next day. We will stop here today. So if you have any questions, please ask. Okay, then if you have any questions, you can ask tomorrow also. Fine. Then thanks everyone. We will continue tomorrow with more details of processes.